Hello, my name is Clara Meister. I'm a PhD student at ETH Zurich, and today I'll be presenting our work titled Revisiting the Uniform Information Density Hypothesis. So, first, I'll present the concept from cognitive science that's central to this work, the Uniform Information Density Hypothesis. Now, the Uniform Information Density Hypothesis states that, within the bounds defined by grammar, speakers prefer utterances that distribute information uniformly across the signal. Where speakers have a choice between several variants to encode their message, they prefer the variant with more uniform information density. In short, this hypothesis tells us that humans prefer sentences that evenly distribute information across the sentence. We don't like moments of high surprisal, as they're hard to process. Now, one commonly cited example of a pressure for UID in human language can be found in the presence or absence of syntactic reduction. So let's take the sentence, "How big is the family that you cook for?" This sentence is also grammatically correct and relays the same message without the word that. But at least for most native speakers, it just sounds better with this relativizer. Now, the information theoretic explanation for this is that without that, the word you conveys two pieces of information, the onset of a relative clause and part of its internal contents. Now, that's a lot of information for one word. Including the relativizer spreads information across two words, thereby avoiding an instance of high surprisal and distributing information across the sentence more uniformly. Now, the concepts of surprisal and information might at first seem vague, but thanks to information theory, we have formal definitions for them. So, given a linguistic utterance, which we define as a series of linguistic units, the surprisal of seeing the next unit is defined as the negative log probability of the token given its prior context. Now, the probability distribution that we're referring to here is the ground truth distribution over a natural language, which we typically don't actually know. But we can approximate it using some language model, such as an n-gram model or a neural language model like GPT-2. So now we've given some informal examples in support of the UID hypothesis. But is there empirical evidence that this pressure for uniformity actually exists in natural language? In short, the answer is yes. And further, these prior works showing support for the UID hypothesis have spanned several levels of linguistic structure. For example, Aylett and Turk showed that there appears to be a relationship between prosodic structure and information content in a linguistic signal, suggesting that prosodic prominence is used to spread information more evenly across a speech signal. Meister et al. Showed that speakers often choose the shorter form of a word when the word is very predictable from context. Yet, all of these examples are in language production. That is, they are with respect to speakers' choices. Consequently, the first question we ask in this work is there evidence of a preference for UID in language comprehension? Or more explicitly, do we observe a preference from those processing language for language with an even distribution of information? Further, these studies have all varied in how they've actually quantified UID in language. Thus, we ask, what is the appropriate way to measure uniformity, or lack thereof, in a linguistic signal? Now, we empirically explore the first of these questions by looking at reading time data and linguistic acceptability judgments. So, given a linguistic signal, we ask, what is the relationship between the effort required to process it and its information content? Now, one common hypothesis about this relationship comes from surprisal theory, which states that the relationship between processing effort and surprisal is linear. Alternatively, the uniform information density hypothesis would imply a superlinear relationship. That is, that the true relationship between effort and surprisal is given rather by some k greater than 1. Now, to see why this implication is true, we look at the minimizing solution of the above equation. For a fixed number of bits, that is a fixed total amount of surprisal in a signal, A uniform distribution of information is the unique minimizing solution, or the distribution that would require the least effort to process. We provide a proof of this in the appendix of our paper for those who would like to see a more rigorous proof. Now, we ask a similar question about the relationship between surprisal and linguistic acceptability. We use the same setup, but without the term for sequence length. And by the same logic as before, if a superlinear function of surprisal is more predictive of linguistic acceptability, then given a fixed number of bits, a uniform distribution of information would maximize linguistic acceptability. To formally test these hypotheses, we look at reading time data in the form of both self-paced and eye-tracking data, as well as human judgments of linguistic acceptability. We fit simple linear regression models to the equations given earlier, including random effects terms for subject IDs when applicable, to control for correlation between data points. Now, our motivation behind this set of experiments is to compare the predictive power of linear models using a linear versus super or even sublinear sum of surprisals as predictors of processing effort and acceptability. If our superlinear model explains the observed data better, this would suggest a preference for uniform information density in text. Now, we determine predictive power by computing the delta in log likelihood of data under a model with and without the sum of surprisals term. Surprisals are estimated using different language models, although we note that BERT only provides pseudolog probabilities, and so these are not true surprisal estimates. That's the red line in this graph. The x-axis here indicates the exponent used in the sum of surprisal terms. And here we observe that k slightly greater than 1 is often just as predictive of reading times as k equals to 1, which suggests that uniformly distributed information could potentially lead to reduced processing effort. Of course, these relationships are purely correlational, and further studies would need to be conducted to confirm any sort of causal relationship. Now, for acceptability data, we see more distinctly that k greater than 1 leads to better predictors of linguistic acceptability, especially when using actual surprisal estimates. These results suggest that a more uniform distribution of information more strongly correlates with linguistic acceptability. Now, the next question we address is how to explicitly quantify uniformity in linguistic signals. So one common interpretation of UID is as a smoothing effect. In other words, a regression to a mean information rate. But this brings up the question, how should we determine this mean rate? And further, how should we quantify deviation from it? Now, importantly, our choices when defining these quantities would determine which distributions of information we deem more uniform. For example, take two sentences with the per-word information distributions given by the red and blue lines. Which of these two should be perceived as more uniform? Under one interpretation of the UID hypothesis, there's a fixed global value from which a unit's information density should never heavily deviate, where we can measure deviation using some distance function, denoted here as delta. Under this interpretation, the red distribution can be perceived as more uniform, since it avoids very large deviations from mu. Yet, we can also look at UID as a pressure to avoid rapidly shifting from information-dense sections to sections requiring minimal processing effort. That is, the local changes in information rate should be gradual. Under this interpretation, the blue distribution should be more uniform, since its local changes are relatively small. Both this global and local interpretation seem plausible, right? So can we formally test which better embodies uniform information density in text? We now look at several operationalizations of UID, each using one of our interpretations and a different distance metric. Similarly to our experiments earlier, we look at the predictive power of these operationalizations for reading times and linguistic acceptability judgments. Under the assumption that uniformity in information density does indeed correlate with lower processing effort and higher linguistic acceptability, which we observe evidence of in our earlier experiments, we would expect that good operationalizations of UID would provide good predictive power. Here, our results show that the linear and superlinear predictors provide the best explanatory power of psychometric data, suggesting that these quantities may best embody UID. And further, we observe that our global interpretations of UID better explain psychometric data, lending initial support to our global interpretation of UID. Now, our final set of experiments looks more closely at this last observation. We explore how the predictive power of our UID operationalization, specifically the variance operationalization, changes as we vary the window sizes over which our mean information rate is computed. Our x-axis indicates this window size, where -1 means solely the information content of the last word was used. Note that this effectively turns our predictor into the local variance operationalization. But as we go along the x-axis, our window size changes from the previous n words to all the words in a sentence to the average information rate of all words in a language as determined by a standard English corpus. We see a general trend that operationalizations with a more global mean information rate are more predictive of psychometric data, suggesting that our global interpretation of UID may be more well-founded. So that's all I have for you. We expand upon all of these experiments and ideas more in our paper, so here's a link if you would like to read more. Thank you for watching.